Recording?
Yeah.
Alright, so this is the remainder of Math 331, lecture, let's say 12, problem solving. So what I want to do is, building on the analysis we just did on that wonderful paper, is talk a little bit about sums of integers. So you've seen this before, we've proven this formula before. The sum of the first n integers is about n squared over 2. Its actual value is n plus 1 over 2. For a lot of problems, you don't actually need to solve. You just want to try to get some rough feeling of what is the size. And if you think back to what we were just doing a few moments ago, trying to get some size, trying to see how wasteful are various assumptions. Can anybody give me a lower bound for this sum? N, right. 1 also works, 0 also works. N is the best trivial lower bound you can give. 1 and 0 are too much of a smartass. N is at least using the largest term. So the sum is at least n. Can anybody give me an upper bound for the sum?
N squared.
N squared. Each term is at most n. So we know the sum is somewhere between n and n squared. The question is, which is it closer to? Okay. So we can prove it by induction. We can prove it by grouping. These are the standard proofs. And then let's try to get a sense of the size. So here is a nice one that does a little bit better. If I look at just the last half, in the last half, each term is at least n over 2. And there's n over 2 such terms. I am never going to care if n is an odd number and n over 2 doesn't exist. I'm not going to worry about that. This is just being casual among friends, okay? So the last half is at least n over 2 terms. Each term is at least n over 2. So I know the sum is at least n over 2 times n over 2. This should actually be an n squared, not an n. Sorry about that. And so we now know that the correct order of magnitude is n squared. We know it's somewhere between n squared over 4 and n squared. And that's not bad. For a lot of problems, you only care about the growth with the parameter. And we got that very fast. Much easier than trying to calculate what the sum was. You could now apply this if I gave you sums of squares or sums of cubes, and you could get a rough estimate of the growth rate. Right. So we can improve. So how many of you have heard of the method divide and conquer? Basically, break a problem into subproblems, solve each one, break the subproblems into subproblems. If you take computer science, you learn to love this idea. Let's break it up into 2 halves, and then in each half, let's do this. Okay? So this is called the Lather, rinse, repeat method. Okay? And so I think what I'm doing here is, to get a lower bound, I break it down into fourths. Going from 0 to n over 4, the lower bound is to use 0. Going from n over 4 to n halves, the lower bound is n over 4, and I have n over 4 such terms. Going from n halves to 3n over 4, I have n over 4 terms. Each term is at least n halves. And then going from 3n over 4 to n, I have, again, n over 4 terms, and each term is at least 3n over 4. And so when the dust settles, you get 6/16 n squared. The correct answer is 1/2. 6/16 is not bad. You could also get the upper bound without too much trouble, and you would be fairly close. So again, this is the power. Without trying to get the exact constant of 1/2, we can get fairly close. And then the question is, could you actually make this method into a proof? At least if n is a perfect power of 2, can you use it to get that in the limit it does become 1/2? All right. I will leave this up for you to ponder and admire the beauty of. Have I talked about this yet? So this is a geometric proof of the irrationality of square root of 2. We will do this at some point. Today was supposed to be geometry day. I will email you guys later as to what we're going to do in terms of geometry day. This is a way to prove, without using the algebra, that square root of 2 is an irrational number. I'm going to stop recording here.